Okay, thank you very much. Good morning, everybody. So, can you hear me correctly? Yes. Okay, so this morning we are going to continue with persistent homology, and we are going to move toward more statistical aspects that are related to data analysis. Just before we start, do you have any question about what we did yesterday, or no specific question? No? Okay. Okay, so let's move a little bit towards more statistical aspects of persistence on TDA. And so if you remember what we have done yesterday, or at least partly, is that we have been considering this kind of general pipeline where you start from some data, typically a point cloud, you build a filtration on top of this data, and then from this filtration, you compute persistent homology. And we have defined persistent homology. We have seen some properties of persistent homology, in particular, a very important one, which that was stability of persistent homology, right? So now what we are going to change, we are going to change a little bit the pipeline by hiding some randomness in the following way. Now we are going to assume that our dataset is not a given dataset, but this is a random dataset. So just to provide a kind of framework, we are going to assume that we have some metric space, M, with some distance rho on it. And on this space, we have a probability measure, mu. And the only condition we put on mu for the moment is that we will just assume that its support is compact, right? And then what we are going to do is that we now assume that we fix M, an integer M, and we sample M points at random in an IID fashion according to the measure mu. So you have a random measure and you randomly pick M points according to your measure mu. Okay? So now what we get here is a random data set. So we can see the filtration that we build on it data set is not random, it's deterministic. It can be for example, the RIPS filtration, the check filtration, the sublevel set filtration of the distance to the point cloud, or anything else. And then we compute the persistent diagram. So now we can see this persistent diagram as a random variable that takes its value in the space of persistent diagram. Okay? And the natural question we can ask when we are in this framework is that what does happen when M goes to infinity? So when I'm sampling more and more points, what does happen for the diagram or the filtration built on top of my M points? That's the question I want to answer. Is it clear? Okay. So that's what we are going to answer in the few coming minutes. And, oops, sorry. So that's a question. And then another question is that when we are in such a random setting, can we do more statistics with persistent diagrams? So we can look at what happens asymptotically when the number of samples goes to infinity. But for example, we now have some random variable. Can we compute some kind of expectation of this random persistent diagram or something like that? Okay, so these are questions we are going to discuss today. Okay, so first, and this is where the stability result will be very useful, because if you remember yesterday, so if filtration here means any filtration like RIPS, check, or something that satisfies a stability theorem. So you can think about the RIPS filtration if you want. And if you remember what we have seen yesterday, is that when you sample, when you have two data sets, or a compact space on the data set, the bottleneck distance between the diagram of the RIPS complex built on top of this data set is always upper bounded by 2 times the Hausdorff distance between these two data sets, okay, or these two spaces. One important thing here is that I'm talking here, so this is not a finite data set, this is a support of the measure. So I assume that this support is compact, and what from the algebraic theory I mentioned yesterday, I showed you yesterday, we can prove as an easy exercise that if you have a compact set, then it's the RIPS filtration built on top of a compact set is always Q10, so it has a well-defined persistent diagram. So that's one. When we go to statistics, that's one first benefit of the general theory, algebraic theory of persistence is that we can talk about the persistent diagram of filtration, Rips filtration built on top of compact sets. Okay? In particular, we can expect that when m goes to infinity, to plus infinity, when you sample more and more points, your set here is going to converge to the support of the measure, and then the candidate to be the limit of this when m goes to infinity is probably this, right? And an immediate consequence of this stability result is that now, if I'm given some epsilon, positive epsilon, if I look at the probabilities at the distance, the bottleneck distance between the diagram of my random sample set and the diagram built on top of the support of my measure is larger than epsilon, this probability is upper bounded by the probability that the outer distance between my random set and the support of the measure is larger than epsilon over 2. And that's a completely obvious consequence of the stability, just a remark after when you have the stability result. But the benefit here is that here we are in the world of persistent homology, etc. Here we are in a world which is much more familiar for statisticians because we are looking at the convergence rate of a sample, a random sample, to the support of the measure that is used to do this sampling, right? This is known as support estimation problems in statistics. It's a very classical area. And we know many things about this. So for example, the first result is that, in fact, the rate of convergence of this diagram, random diagram, to the limit, to the diagram of the support, will be in fact driven by the rate of convergence of the sample itself to the support of the measure. And for example, if we assume if we make some kind of regularity assumption about the measure mu, so now we not only assume that it has a support compact, but we also assume that the measure is what we call AB standard. And AB standard is the following, is that we assume that for any point x in the support of the measure, when you look at the measure or the probability of a ball of radius r, you look at this measure to grow at least polynomially as a times r to the b. Okay, if your measure has density, and if you are on a space of dimension b, your measure, and if the density does not vanish, your measure will be AB standard. So you can think about B as like a kind of dimension if you work with density, with measure with density with respect to. Okay, is that clear? So this is a classical assumption. And now, if you suppose that your measure is AB standard, you very easily get a deviation inequality. So you get that. So you are given m and epsilon. When you randomly sample m points according to mu, and you look at the bottleneck distance between the diagram built on top of the support of the measure and the diagram of the filtration built on top of your random set made of m point, the probability that this quantity, this distance is larger than epsilon, in fact, is upper bounded by something like 1 over epsilon to the b times exponential minus some constants times m, epsilon to the b. Okay? So if m is fixed, if epsilon is fixed, you have an exponential rate of convergence of this. Okay? This is a standard deviation inequality. And the way you prove it is a very classical way to prove this kind of inequality. I don't know if I plan to give you the proof, but no, in fact, I don't. Yeah, but the idea here to prove this kind of result in general is that you cover the support of your measure mu by a minimum. You look at what is called the covering number of the support of mu. So you look at the smallest number of balls you need of radius epsilon. You need to cover the support of mu. And then this, as you have an AB standard measure, you can upper bound this number of balls that you need explicitly. And then after that, you look at what is the probability that when you sample m point, you miss one of the ball. Because if you have 1 point in one of the ball, the distance, out of distance between your sample and the support will be upper bounded by epsilon, and then you will be able to apply it. So you look at the other event, which is that you look at the probability that you miss one of the balls. So you could potentially have a distance which is larger than epsilon, and this is controlled by some exponential terms like this. It's a very simple exercise. And yes? A/B standard.
Does say something about the conversions of the front of house of distance? Like,
the thing is that you will always have convergence towards the support, but in fact, the rate of convergence will depend on some property like that, or if you have a measure with density on its support, it will depend on how the density decrease to zero. So you can write, in fact, what you need at some point, the key ingredient here is to be able to control the covering number of the support. And the idea is that you have a relation between the covering number is upper bounded by what is called the packing number of the support, which is the maximum number of balls that you put centered on the support and that do not intersect. There is a connection between both when you multiply the radius by 2. And then when you look at the packing number, because you are A/B standard, you cannot have too many balls in the centered on the support that do not intersect in packing number because you have a probability measure. So as each ball of radius r has a weight of at least a times r to the b, the total number cannot be larger than 1 over r to the b. And then you use this to get an upper bound on the covering number, etc. So as soon as you are able to control the radius of the balls on the way, you will be able to get something like that where you change. Okay? So it's a very, all this is very simple application. The stability theorem is a non-obvious theorem, but all this is a really easy exercise. And when you have a differentiation inequality, you can also get what is called minimax rate of convergence for the estimation of the diagram, the persistent diagram of the support of X mu. And in fact, you have the following result that tell you that now if I look at the set of all the probability measures that are defined on M and that are A/B standard, okay, with compact support. Then when I look at the expectation now, so I sample M point at random, I get this distance. So I look at the distance between the diagram built on the top of the M point and the limit diagram. I look at the bottleneck distance. This is a random variable. So I can look at the expectation of this real valued random variable. And I look at the supremum of this expectation over all the possible way to sample according to a measure mu, which is A/B standard, right? And this supremum is always is upper bounded by something in log M over M to the 1 over B. So you know that whatever the measure you choose, as soon as it is A/B standard, the expected bottleneck distance between the diagram built on top of M point and the limit diagram is upper bounded by log M over M to the 1 over B. So we get an upper bound on the convergence rate. And in fact, don't waste too much time to read this. It's a bit technical. But what this part tells you is that, in fact, this upper bound is the exact rate of convergence in the sense that you can also prove that whatever the way you estimate this diagram from a random sample of M point, you will never be able to find an estimator, an algorithm or whatever, that has a better rate of convergence than this one. So whatever the way you estimate these things, for example, if you don't use the estimator we use, that is just to compute persistence of the filtration on the random point, you will never succeed. You will always be able to find some measures in this family for which the rate of convergence is at least this. This is what we call a minimax rate of convergence, because for this quantity, we have here an estimator of this quantity that has a rate of convergence which is optimal in this family of AB standard measures. Okay? Again, that's just classical statistical stuff applied to persistence with the help of the stability result. Okay? So far, so good? Any question about this? No? Okay, so now we are quite happy with this first step towards statistical aspect of persistence, because we know, at least in the setting we just defined, that when you render some m point according to measure mu, when the m goes to infinity, you will converge to the diagram, the persistent diagram of the support of your measure, and we even know the rate of convergence as soon as we are considering measures that are sufficiently regular. But now a question is that, can we do much more when we stay in the space of persistent diagram? For example, in general, when you do statistics and look at random variable, you like to be able to average, to compute averages or expectation of random variables. Here, we are living in the space of persistent diagram, which is endowed with a bottleneck distance. So this is a metric space, but I think that this is a very, very bad space from the properties of the space. It's very far from a linear space. Everything is going wrong in this space. It's very clear. It's not a nice space to be, or not a nice space to spend your vacation in. You know, that's for example, if you try to define what would be the expectation or the mean of a set of persistent diagrams, it's not completely obvious because you don't have a linear structure, so you cannot define it as a barycenter. You can try to do what is called Fréchet-Min. I don't know if you are familiar with this notion of Fréchet-Min, but for example, in the Euclidean setting, when you look a set of points and you look at the average of this set of vectors, so this is a barycenter, and in fact, the barycenter is a solution of a quadratic problem. This is a point that minimizes the sum of the distances to all your data points, right? The squared distances, sorry. So when you are in a metric space and when you don't have a linear structure, you can try to define what is called the Fréchet-Min by using this definition by saying that when you have a finite set of diagrams, you could try to find a diagram, or a diagram that will minimize the sum of the squared bottleneck distances to each of your diagrams, right? But the problem is that in this space of diagram, you can try to define this. By adding a few constraints, you can prove that such a minimum exists. But the problem is that even on very simple example, this minimum is not unique. Even for two diagrams, if you try two simple diagrams with 2 points each, you can imagine a configuration where you have an infinite set of minimizer of this function. So you are not in a nice, it's not a nice world in which you could do this kind of things. So that's one of the motivations to do what we discussed a little bit yesterday afternoon. That the question is now, can we try to embed the space of diagrams into vector spaces to find vectorization of the persistent diagram in such a way that we can continue to do statistics? Because if we are able to embed the persistent diagram into a vector space, right, then in this vector space, we will get a new representation of persistence, and we can compute averages, and do all the classical statistics that you can do in vector spaces, right? And we have discussed a few possible vectorization yesterday. And what I'm going to present now and what we are going to work with is probably one of the first very clever way to vectorize persistent diagram, which is called persistent landscape, and that was introduced by Peter Bubnik like a little bit more than 10 years ago. And it's not a completely intuitive way to embed persistent diagram into vector space, but as you will see, it's interesting because this is an injective way to embed persistent diagram. So the map that goes from associate to a persistent diagram, it's what is called persistent landscape is injective, and moreover, as we will see, it preserves the stability properties of persistent diagram. So how do we build the persistence landscape? So a persistence landscape will be a family of functions defined on the real line, taking its real value, indexed by the integers, or natural integers. Or if you prefer, this is a function on R cross N, where N is a set of natural integers, okay? And the way we do it, I'm just going it by hand, is that you start with a persistent diagram D, and the first thing is that you first rotate your diagram by 45 degrees, just to put the diagonal horizontal, okay? And for each point of the diagram, you can look at this triangle here, which before rotating, you could look at this triangle, which is a rectangle triangle, isocele, with a right angle here, okay? That joins the point to its vertical and horizontal corresponding point on the diagonal. And I do that for all the points. So when I'm rotating, I get a set of possibly overlapping triangles. And the way you define what is called the first persistence landscape, the first persistence landscape will be the function, which is in blue here, which is, when I don't draw it, it means that this is 0, which is in fact the upper envelope of this set of all the triangles. So you can see this triangle as many overlapping mountains, and you look at it from far away, you see the horizon, and the horizon line is the graph of the first landscape. In particular, this is a piecewise linear function where each piece has slope +1 or -1, except when this is 0 outside the support of the function. Okay, so this is the first persistence landscape. And now, when you have the first persistence landscape, you look at the second persistent landscape, which is the horizon that you see when you just look at the places where you have at least 2 mountains or 2 triangles that overlap. So this is here the red part. So this is the graph of the function, which is defined as the upper envelope of the intersection of at least 2 triangles, right? Is it clear? And then you continue in this way. You get the third landscape, which is the upper envelope of the set of where you have at least 3 triangles that overlap, and then you stop when you don't have anybody else. Okay? So you get in this way a decreasing family of functions that are piecewise linear with slope +1, -1, or 0. And if you have a finite diagram at the beginning, this is a finite family of functions. Yes?
Die in finite time, the assumptions of the program to be pretty important, but this doesn't capture anything that doesn't die in finite time.
Okay, that's a very good question. In fact, here, what I'm hidden is that the fact that in a persistent diagram, we can have some infinite intervals or point with infinite y coordinate, okay? So in general, what we do in practice is that when you work with a filtration like the RIPS, at the very end of filtration, in any case, you have only one point at infinite because all homology is killed before the end. So in general, what people do is that they separate this infinite part of the diagram from the finite part. Because if you would have to put an infinite triangle, in some sense, your first landscape function would be plus infinite or something like that. So you just discard it and you keep this apart. So here, I forget about this. This is a small technicality, but you have to take about it in practice. But what we do here, just to avoid these technicalities, we forget about the points that are at infinite. Okay, but that's a very good remark. Okay, so so if you want, in fact, to define this a little bit more formally, you can just define that this triangle seen in this rotated coordinate system are just some kind of tent function that are defined with this formula. You know, this is a piecewise function, a linear function. And for each point P, you have one, you call it lambda P of T. And then you say that the chaos landscape, the value of the chaos landscape at T is just what we call the K-max. So this is the K's largest value. So you start from the largest and then go up to K among all these tent function. Okay, so for the landscape, first landscape, you get the max of these functions, and for the second landscape, you send the second max, etc. Okay, so this is something which is very easy to compute in practice. It's almost instant. You can get this represent immediately. There is no cost. Yes.
Still need exactly the same number of coordinates to describe.
I did not claim that this reduces in any way the complexity of the diagram.
Consider this a collection of all points in the upper half, in the upper triangle, and it's also a vector space if you consider point points.
What? Yeah. Yeah. You cannot, in fact, the diagram in itself, there are many ways to vectorize persistent diagram, but the way you are saying that we just list the points is not a way to vectorize because you cannot, it depends, the dimension of the vector will depend on the number of points if you do that.
No, I just meant like take R2 to the, like R2 times R basically as a vector space.
But
so for each point in R2, you basically have R, and then for each point in R2, you discount the number of the multiplicity. I mean,
you see that just as a function in R2 where
exactly.
That's a way to do it, but it's not a way where what is a so first it's a what is a metric you would put, for example, on this vector space, because this is you are now in the space of a function in R2, and it's not even the continuous function. So what kind of topology do you put on the? So you which? No, because this is going to be very unstable, and all the points will be at distance, very large distance from each other, all the diagrams. In fact, but you are not very far from something we will see later, which a better way to do that would be to say that we can see diagrams as discrete measure in the plane, and in that case, they would live in the space of discrete measures, which is not a vector space, which is just a kind of a cone, or if a convex, no, it's a kind of cone in some space, but it's not, we will see that this point of view of measure, seeing just as measures to do some different things. But here, and there is not a unique way to vectorize, but this is not something that is very convenient to get some stability result on this kind of thing. This is completely different because here, to a diagram, I convert a diagram into an element of a functional space, which is just a space of functions in fact, this is a space of piecewise linear, or let's say that this is a space of Lipschitz function with consequences from R times N to R. Okay? And here I have a metric, I can put the sup norm or the L2 norm or whatever. Okay, but keep your remark in mind because we will see this idea, but with a measure point of view coming back later. Okay, good. So did you get the definition? So now the benefit of this is that first obvious remark is that this family of functions you get over R is decreasing with K. The Ks landscape is always below the K-1s landscape. And one important property is that this the map that goes from the persistent diagram into the space, this space to the landscapes. If I put the sup norm here, this map is going to be one Lipschitz. So the difference between the landscape as and K and T, if I look at the difference between the lambda D and lambda D prime, if D and D prime are two persistent diagram, it is always upper bounded by the bottleneck distance between D and D prime, which means that all the stability result we stated for bottleneck distance still hold for landscapes. And I did not wrote it before, but also it's quite an easy exercise to check that this embedding of persistent diagram into the space of function is injective. if two diagrams are different, you get two different landscapes, or if two diagrams get the same landscape. When you get the landscape, you can recover the persistent diagram quite easily. Okay? So that's the interest of this way to vectorize, because we map the persistent diagram into vector space, in fact, even a normed vector space. And this mapping is injective, and we preserve the stability properties. And and now with this, we are quite happy, because now we are living in a vector space. So if I have a set of diagrams, I can look at the set of corresponding landscapes. This is a set of functions. I can average these functions to get an expectation, right? But that's nice. That's an advantage. But there is a small drawback that you have to keep in mind, is that the way you embed the space of diagram into this space is not linear. So you don't get, it is not a linear space, it's not even a convex set that you get as the image of the diagram in this space. So when you average a set of diagram, you get a function. So as you average a set of Lipschitz function, you still get a Lipschitz function, one Lipschitz function, okay? But the problem is that this one Lipschitz function is not the landscape of a given diagram. So when you average, you cannot come back to, there is not a diagram associated to this average. So this is a price you have to pay to linearize persistent diagram and to do some averaging extra, is that you can do all this, but you go out from the space of persistent diagram. Yes?
Landscape. How do you tell the difference between zero-dimensional homology features and one-dimensional?
In general, so that's something I should have said a little bit more clearly yesterday. In general, what you do is that you separate so when I'm talking about, I'm saying the persistent diagram of this filtration, I should say the persistent diagram of a given dimension of this filtration. You always separate the dimension. So for example, if you look at a function, you have the zero-dimensional persistent diagram, the one-dimensional, etc. And you do not compare one-dimensional feature with two-dimensional feature and this kind of thing. Okay? So in general, you have one landscape for each dimension. So we can do we can compute averages. If we have a distribution of persistent diagram, we can look at its expectation. And in fact, we can even do, I won't explain this because it would need to go through some aspect of empirical processes, but taking a process point of view, seeing this, when you have a distribution of a persistent diagram, so you can see it as a distribution of landscapes. And if you see the distribution of landscape as realization of some process, random process, you can do some bootstrap and you can prove some convergence result for the expectation of your distribution of landscapes. So you can look at the expectation of this distribution and you can prove that by some bootstrap technique, you can estimate this expectation from a finite set of some sampled landscape. And you can even do that with confidence intervals. Okay, just I don't. Oh, I have forgotten to put. I show you some example of average persistent landscape in a moment. And also, as we are also living in a now in a vector space, we have a vector representation, even if it's finite one. It opens the door to use this persistent information through landscape for further machine learning tasks. And for example, it was used to design some neural network, or at least some neural network architectures that are able to process persistent diagram by first converting them into landscape and then process as input these landscapes seen as functions. There are a few papers, maybe several papers about this. With different variants to do that. There are many ways to do that. Okay? Is that clear? So now, if I'm coming back or try to summarize a little bit what we have seen up to now and because I want to show you also another nice property of this distribution of persistent diagram and thus seen as a landscape, is that if I try to summarize, we had this pipeline that go up to persistence where we randomly sample endpoint. So we have seen that if we randomly sample endpoint, look at the filtration on top of them and look at the random persistent diagram, when M goes to infinity, we converge to the persistent diagram of the support of the measure mu. And if n has stabilities preserved by landscape, the same holds for landscapes. If I just consider the landscape instead of looking at the persistent diagrams, right? I have the same convergence result to the landscape of the support of my measure. So that's when M goes to infinity. But now another idea is that if I fix M now, and I do some kind of subsampling or bootstrap, so instead of taking M going to infinity, I can repeat my experiments n times. So I choose an n, and n times I sample M point, I compute a persistent diagram, a persistent landscape, and I get a family of n persistence landscape. Okay? So now what I can do is that I can look at the average of this family. And what I've just mentioned before, but did not state formally, is that this empirical average of my distribution of sample landscape converge to some expectation, which is just the expectation of this random variable landscape, right? So when n goes to infinity, when I repeat my experiments many times, the empirical average of the obtained landscape is converging to some object, which is the expectation of my distribution of landscapes, right? And it's not difficult to see now if I take this limit. And so this is done when M is fixed. If I take M is going to infinity, I will go back here, converge here. That's easy to check. But there is one remaining interesting question, is that, and that is related to something we said yesterday. If you are sampling according to mu, but sometimes you had an outlier, but not too often. It's like sampling according to another measure, which is a little bit different from mu. And we could ask what happened to this expectation when I do this sampling of M point at random and I repeat, because in many cases, I won't sample the outliers and I will get something that look like this landscape of mu and not the perturbated one. And by averaging, I could expect that I will decrease the effect of the outliers. So if I want to formulate this a little bit more clearly or more mathematically, is that what does happen to this expectation when I change the measure that I use to sample? If I perturbate a little bit the measure mu that is used to sample, do I change a lot this quantity? Do I have a stability result for this quantity? And that's something that will make, if I'm able to state something about this, I will get a way to get some topological information which is more robust to outlier than the stability result we have stated yesterday. Right? Yeah?
Is there something bootstrap, or is this exactly what bootstrapping means? Because I don't know the term bootstrap.
Okay, don't worry about the term bootstrap. Just the idea here is that either you have a way to sample many times endpoints, but in practice, sometimes you have a huge data set that might be polluted with some outliers. And instead of trying to compute the persistent diagram of the whole filtration on the whole data set, what you do, you choose an M, like 1000, you sample at random M point, you get a persistent diagram, you look at and you get a persistent landscape, you repeat this n times, and then you now have n landscapes, and you take the average of this n landscape, and your hope is that by doing this, you will going to smooth a little bit things out, so you will lose a little bit of information because we'll get an average of landscape, not a very nice landscape, but you will do, if in some sampling you get outliers, if this does not happen too often, the expectation or the average of landscape should not reflect too much this, the presence of these outliers. In some sense, it's a way to decrease outlier. It's also a way to get something when you have a too huge point cloud and then computing the whole filtration would be too expensive because here you choose M. So if you know that you are able to compute efficiently your Persistent diagram with M point, let's say M equal 100, when M equal 1000, you can repeat this, parallelize it, and get control the computational resources you will need to get your result. Yeah, there is no optimization in it, but yeah. There are the landscapes of, you can see, you can look the first landscape if you want, but you can look all the landscape at the same time, just as seeing them as a function from R times N. It's, okay, it's clear? Okay, no more question about this? So now we want to study the stability of this object with respect to the perturbation of the sampling measure, right? And for that, what I need is that I need to put a metric on the space of measure, because I need to say that when two measures are close to each other, these two things will be close to each other, okay? And the natural candidate for the metric between these probability measures is the what is called the Wasserstein distance. I don't know if you are familiar with Wasserstein distances. No, who does not? No. These are classical. Now they are very popular now because of the huge development of optimal transport during the last years. But this is one. So there are many metrics you can put on the space of probabilities. There is a total variation metric, Ellinger metric, etc. But one that can, the benefit of the Wasserstein distance is that in some sense is C. This is a metric that is sensitive to the topology, not the topology, but the metric of the underlying space. So just to give you the definition in a few words. So this is, maybe you have seen this sometimes, this example. This is a metric that measures the cost that if you have two probability measures that you can see as two distribution of mass in some metric space, and you decide to have a cost when you move one unit of mass from one point to another. You have a cost function which tells you how it costs to move this unit of mass from a point X to a point Y. In Euclidean spaces, for example, it's classical to use the distance, the Euclidean distance to the some power p. And now you try to find the optimal way to transport the distribution of mass of the pressure measure to the distribution of mass of the second one by while you minimize the cost at the minimal possible cost. If you say that in a more mathematical framework way, you have to define what is a transport plan, what is a way to transport the distribution of mass of a measure to another one. The way to do that is to define it as a measure, a probability measure on M times M. And you ask this probability measure to have its two marginals on each copy of M to be one to be mu and the other one to be nu, if you are trying to do a transport plan between two measure mu and nu. Okay? So this is what is written here. When you look at the probability of a cylinder of the form A times, I should have put M here, sorry, there is a mistake, and the same here, M times V, you get on one coordinate the measure mu of A, on the other one, the measure nu of B. And when you look at the pi of A times B, this is, you get the amount of mass of A that is moved to B. Okay, so if you give this description, in fact, you describe the way to transport mass from one distribution to the other one. If you are in the discrete setting, you can think of a transport plan as a matrix. So if you have a finite measure mu, which is just a finite sum of weighted Dirac, and a finite measure nu, which is just a finite sum of Dirac, to define a transport plan, you have to say, okay, on the first atom of mu, I have a total mass of C1, and I have to decide how much of C1 I move to each of these points that are in the support of nu. Okay, and I do that for all the points here, the atoms here. And when I'm doing this, I'm building a matrix where when I sum up the columns, I got this weights for the mu, and when I sum up the lines, I get the weights for nu. All right? Is that clear? The idea? So a transport plan is just a way you take the mass, the distribution of mass for one of the measure, and you say this part of mass is going there, there, and there. And then the cost of a transport plan is just that for when you move a unit of mass from one point to the other, the price you have to pay is this unit of mass times the cost of the transportation from one point to the other. In the case of the matrix representation, this is just a sum of the term of the matrix multiplied by the distances, or the cost. For a continuous transport plan here, this is what you are doing. You are just integrating so here I'm taking as a cost the distance to the p, and the cost is just the distance to the p between x and y times the amount of mass, infinitesimal mass, I move from x to y. Right? And then as I take a power p here to be homogeneous to the distance, I take one of the p here. And what is called the Wasserstein distance between my measures mu and nu is just the infimum over all the possible transport plan of this cost. Just let me show you a very simple example that will give you an idea why I like this distance for what we are doing. Is that suppose that I have two measures now, just an example. These are in R2, these are discrete measures. So the first one is the sum of the Dirac, which is made of the black points, black atoms and red ones. And then I take for the second measure, nu, I take exactly the same point cloud, except that I take the red point and I move them far away from the black points, and I move them at a distance which is some constant r, which is potentially very large. Okay? And now, if I look, and I see this as two empirical measures, the weighted sum of the Dirac on top of this point. Well, there is an obvious transport plan between these two measures, which is the one that does not change the mass at the black point and just brings the blue point back to the red point. So if I look at these 2 point cloud as sets, and if I look at the Hausdorff between these 2 point cloud, the Hausdorff between these 2 point cloud will be at least r, because there are some point, the blue points at that distance at least r from the set of black and red points. Okay? And now I have, if I look at this as measure, I have an obvious transport, I have this obvious transport plan I just mentioned to you. And the cost of this transport plan is that for each of the blue point, if I have move k blue point, they all have a mass 1 over n, if n is the total number of points. The price I have to pay to bring one blue point back to the red point is at most r plus the whole diameter of the point cloud times the mass, which is 1 over n. Okay? Here, if I'm taking p equal to 2, so now I do that k times. So the total squared cost is just k over n times this distance to the square. When I'm taking the square root, I get that the Wasserstein distance between, for p equal to, between these two empirical measures is upper bounded by some constant times the square root of k over n. So here I have something of order n. If here I have something of r, of order r times square root of k over n. So if the number of outliers, if you see this color point as outliers, blue color point, that I've moved, I need to move back, is small with respect to n. You see that as seen as measure in the Wasserstein metric, these two empirical measures are close to each other. So the Wasserstein distance, in some sense, if you perturb a measure by adding some outliers or empirical measures, if you do not add too much outliers and if you don't send them almost at infinity, from a Wasserstein perspective, these two measures will be very close to each other, while for the Hausdorff distance, you get something very large. So that's one of the benefits of the Wasserstein metric, at least for us. Okay, question about this? So now, with this Wasserstein distance, and I will conclude on this, I can state a stability result. So I am in the following setting. So I have my whole pipeline. I should choose an integer m. Let's say m equal 100 or 1000. And I do my construction where I randomly sample m point, I repeat, and I look at the expectation. So if I sample according to a measure mu, I call lambda mu m of t the expectation of the landscape that I obtain by doing this. Okay? And now, if I sample according to measure mu on nu, I get a lambda m, a lambda mu m, a lambda nu m. Okay, m is the number of points I sample. These both are functions on r times n. Okay, these are expectation of functions, they are still functions. So I can look at the subnorm of the difference between these two expected landscapes. And these things is upper bounded by the Wasserstein distance between the two measures times some constant here, which is m to the 1 over p. Okay, so if m is fixed, I get a stability result that tells me that if I perturbate my measure mu a little bit in the Wasserstein metric, I won't change too much the average landscape I will get by sampling randomly m point. When you see this result at the first time, you may feel a bit annoyed because here you have this constant, which is depending on m, and it goes to infinity as m goes to infinity. And so there are two remarks to make about this. The first one is that if you cannot do better, this result is not something that you have to see as a result with some interest from an asymptotic perspective when m goes to infinity. Because as m goes to infinity, this quantity goes to infinity, and then you lose the stability. So you have to use this result with some kind of not too large values of m. And the second question is that, do we really need this question? Is it optimal? So I don't know if it's an optimal constant, but what I can easily see is that whatever the constant is here, it will depend on m, and it will have to go to infinity when m goes to infinity. And you can easily build examples, in fact, where when you look at this, the ratio between these two things and the Wasserstein distance goes to infinity as m goes to infinity. It's very easy to build example. And more intuitively, more waving my hands, if you think a little bit about it, when mu and nu are fixed, the Wasserstein distance between nu is something that never changed. Okay? But when m, so this is associated to the measures themselves, and you need, but now, if you look what these two objects, when m goes to infinity, they converge to the landscape of the support of the measure mu and the support of the measure nu, which are a topological object. These are just subset of a metric space, and this subset forget something about the measure. They just keep as information the support of the measure, but not the way the mass is distributed on its support. Okay? So at the limit, this is a purely topological object, while here you keep a measure object. So in some sense, at the limit, you compare some objects that cannot be compared, right? And when you think about this, it's very easy to do some example because you just need to make some example where the Wasserstein distance between the two measures is very small, but the supports have a very different topology and can be very far away from each other. And this is very easy to do. Just think about it. We can do it as an exercise if you want later, but that's the idea. And as I'm done, almost done, just a few consequences, practical and interesting consequences. So because of this, when you look at the expectation of the landscape, you get something which is robust to outliers that in some sense partially circumvent the problem we raised during the discussion yesterday about the Hausdorff stability, which is very sensitive to outliers. So here, when we consider this object, we get an object which is much less sensitive to outliers. computing this kind of things or estimating this kind of thing is very easy because you are the one who choose M. So you're interested to choose M not too large so that you are able to efficiently compute persistent diagram on top of M points. And you can, and to get the average, you can parallelize this very easily. You don't need to, you can compute the N different, the persistent landscape of N different samples of size M in parallel. There is no problem. And if you want to play a little bit, there is some, I think there is some implementation in different packages of this, but this is very easy to do by hand. There is nothing difficult. And one word about the proof. In fact, the proof is quite elementary. It's just like 1 page or something like that. It's a very basic property of about the Wasserstein distance between tensorized measures. So when you have the distance between mu and nu, when you sample M points according to mu, it's like sampling 1 point according to mu tensorized M times, and the same for nu. So you have a control, you control the Wasserstein distance between this tensorized measure with the Wasserstein distance here. This is where the coefficient appear here. And then after that, you have to play with the this is one application of the stability of persistence plus one application of the Jensen inequality, some convexity argument. But the proof does not, you have to find it, but once you have it, you don't need some very deep result, except that you, again, this is a stability for persistence theorem that give you this result. Just, I can maybe just show you an example or numerical illustration. For example, if you have, suppose that you have two point clouds, the one which is just made of the black point on the circle, on some circle, and the second one is the same, but you just had one outlier, which is the center of the circle. So if you look at the persistent diagram of the black and the red, the one-dimensional persistent diagram, here you see that for the red, black, you will see one cycle, and this cycle will die at something that is not, I don't remember if I took the distance to the point cloud or the rips, but it will die at something which is comparable to the radius of the, maybe not, or 2 times, or square root of something, but related to the radius. If you put the point in the middle, as you will grow a ball in the middle from the beginning, you will fill this cycle much earlier, and then you get the red persistent diagram. Okay, so the persistent diagram are very different if you look at the whole point cloud. If you look at this in terms of landscapes, you get the this landscape for the black point cloud, and the black plus outlier give you this landscape. They are very different. So one outlier pollute completely the signal. And if you now do the look at the expectation by subsampling, I don't know how many points I subsampled here, but typically what you get is that now you get the dashed curve for the average landscapes. And as you see, the difference between the black and the red is no longer that large. In both cases, you still see quite well the presence of the cycle. That's a very simple example. Another example where sampling was done in different spaces. So we change the measure by sampling. So the spaces were surfaces here, animals. We sample randomly M point on an elephant, a camel, pink flamingo, and a tiger, lion, or I don't know what. And then I put here, what you see here are the expected landscapes in dimension, I guess, 1. So here we average 100 landscape from samples of size 300. And what you have here, the small interval, are confidence intervals that you can compute around the average. Because of some things I did not develop that I mentioned before, we can estimate this average landscape, but also with confidence interval. And as you can see, these animals have quite different expected landscape. That's just an illustration. That's clearly not the best way to make the distinction between these 4 animals. Okay. In particular, if you are in front of a lion, don't start to tell him, I'm going to sample you several times and compute average landscape to be sure that you are a lion. This could be a sad story. I will stop here. That's another example where with more real data that was done with multivariate time series, and that was just a game. We recorded some inertial data from smartphone where by 3 different people, and we tried to see if from these samples, signal samples, that was I think it was acceleration or something like that, we were able to distinguish. We asked these 3 people to work around in some building. And then we computed the average landscape to see if we were able to distinguish these people from their average persistent landscape. So that was just that's clearly not the best way to try to recognize people from their movement, but that's just a kind of illustration of what's going. Okay, so let's stop here for this morning. If you